Welcome to the SEI Podcast Series, a production of the Carnegie Mellon University Software Engineering Institute. The SEI is a federally funded research and development center sponsored by the U.S. Department of Defense. A transcript of today's podcast is posted on the SEI website at sei.cmu.edu/podcasts.
Welcome to the SEI Podcast Series. My name is Jonathan Spring, and I'm a senior vulnerability researcher here at the SEI CERT Division. Today, I'm joined by two illustrious colleagues, Dr. Grace Lewis, principal researcher and lead of the Tactical and AI-Enabled Systems Initiative here at the SEI, and Dr. Ipek Ozkaya, technical director of the Engineering Intelligent Software Systems Directorate, also here at the SEI. Today, we're here to discuss their research in software engineering for machine learning. Welcome to you both.
Thank you.
Thanks.
Great. So, Grace, Ipek, can we start with telling our listeners a little bit about yourselves and what brought you here to the SEI?
Sure, I can start. My name is Grace Lewis. I came to the SEI, hard to believe it, but 20 years ago, after completing my Master in Software Engineering at Carnegie Mellon University, I joined as an engineer, meaning that I was a software developer on several projects that were ongoing. Very quickly, I learned that my passion was really the research. I mean, I like engineering, but my passion was really the research side. So after that, I got a PhD in computer science from the Vrije Universiteit in Amsterdam. And now at the SEI, I lead an initiative, like you said, called TAS, Tactical and AI-Enabled Systems, where we conduct applied research and development in three focus areas. One is tactical edge systems. The second is software engineering for AI systems. And the third is the intersection of the two, meaning how do you do AI at the edge?
Great, thanks. Ipek, how about yourself?
Well, thanks for having us, Ipek Ozkaya. And I came to the SEI longer than I actually can admit to myself, around 2006. This was right after I completed my PhD at Carnegie Mellon University in a field called computational design. That was applying software engineering to design professionals and to architecture and design tasks. But I was very passionate about software and its research. And ever since I joined the SEI, my focus has been on software architecture and combining software architecture practices and applying it with organizations. My current research is focused on understanding how to manage technical debt, again, which builds on architecture and software architecture principles, and also with working with Grace and our other teams on understanding what software engineering for AI-enabled systems look like.
So, thanks. I know building on both of those pieces of work for ML systems, you two recently wrote a blog post exploring software engineering in ML and characterizing what you call mismatch in ML systems. So how does this problem of mismatch come up with machine learning, and can you describe the sort of entry point for the problem for why we care about it?
Yeah, sure. So the origin of mismatch is that when you think about how machine learning systems are built, they're built by three different types of teams. You have data scientists or machine learning engineers that are building machine learning models. Then that model is typically passed on to a software engineering team for integration into a larger system. And then the system itself is kind of passed on to an operations team that now is in charge of operating and monitoring the system as a whole. The problem is that if you look at how these teams are composed, very different people, very different backgrounds, very different vocabulary, and in the end, also very different system concerns. So what happens is that these teams, because they also operate independently, unfortunately, tend to make assumptions about what the other parts of the teams in the systems are doing, and that is what leads to mismatch. So basically, mismatch is a problem that occurs because of an incorrect assumption made in isolation by one of these teams. And in addition to that, if we've found that you can trace the cause of the mismatch to something that some piece of information that should have been shared between stakeholders, and if it would have been shared, it would have avoided that problem.
Great. So I'm sure that misaligned assumptions are not totally new, but Ipek, could you talk a little bit about how the mismatch sort of shows up from traditional software engineering and how that gets maybe worse in machine learning systems?
Of course, and as you've identified, mismatch is not new to software engineering systems and actually any engineering system. It's really the assumptions that different parties make and how you communicate those assumptions. What's different is in the software engineering systems, we have techniques that we actually anticipate, and we've kind of safeguarded with it. What has been catching a lot of the organizations who are developing now ML-enabled systems unprepared is the data scientists, the new set of technical stakeholders that are joining the development of these systems. First of all, maybe making different assumptions. Their techniques are different. The way they measure success or how the elements that they develop, like the ML models are developed, behave are different. And these models go through so many different stages that software engineers may not always appreciate. So putting that together, there are actually new categories of mismatch or mismatch assumptions that occur, and also maybe opportunities to safeguard the systems, both with automation or other techniques. And that was the observation that we made, and that's how the research started.
Yeah, of course. So I want to, I think that we'll want to talk to what we might recommend people can do to safeguard against different kinds of mismatch, but it's clear that we need to know what they are before we can safeguard against them. So can you tell us a little bit about how you would go about methodologically sort of characterizing the new kinds of mismatch, and maybe also interesting places where you've identified the sort of the same mismatch is maybe more impactful, but like how would we go about studying this?
Let me get started. The approach we took was an empirical approach. I mean, there were some observations we had started to make based on the organizations we worked with, things we read, our research and whatnot. But we stepped back and say, okay, what does a mismatch really look like? And do these mismatch appear same way from a data scientist perspective, from a software engineer perspective, from an operations individual perspective? So we interviewed individuals across the board that included a combination of these different expertise levels, and we collected their examples. And then we also supplemented that information with things that have been written. There are quite a number of actually papers now coming out from experiences, Microsoft, Google, and some of these organizations who are doing it. And there are examples there as well. So, and as a result, there were about 140 examples of mismatch that we've collected. And then we went about with a characterization or exercise to see whether there are some categories that are emerging. And that kind of started snowballing the research.
Great. So I think that that's a really great example of sort of mixed methods, sort of, I guess, social science and general research, which is super important and I think underused to understand, at least the security side of things. I'm not as expert in software engineering, but is that also something that maybe people need to do more of for software engineering?
I would say so. So it, like Ipek said, and like you said, it is definitely a mixed method study. So in one part of it was understanding from real practitioners, what does a mismatch look like? Or even like that was a hypothesis that we had, right? But is this real? Does mismatch really happen, right? So that was the part of the interviews that we also validated with a survey. But in parallel to that, just as Ipek said, we said, you know what? Mismatch has occurred in the past. There are lots of kinds of mismatch. Let's look at what the literature says, and maybe are there best practices out there already for these types of systems? And so we conducted what is called a multivocal literature study, where you look not only at the white literature, which is the academic literature, but you look at the gray literature, which is basically what comes up when you Google something, right? So like more informal blog posts. And the advantage of that is that you get the academic perspective, but you also get the industry perspective, because those are the folks that are writing the gray literature. And so then after that, what we did was basically a mapping, right? We said, okay, we know that all these mismatches exist. Which one of these best practices can we map to those mismatches? And then we ended up with a really, really nice matrix. And then at the end, what happened is that all that information that should have been shared, we codified it into a set of descriptors. They're machine readable. And so these descriptors are parts of the system. So this is how you describe your trained model. This is how you describe your raw data. This is how you describe your training data. This is how you describe your operational environment. Because that way, that information now is explicit. It's shared. And the goal of making the machine readable is that our next steps are really to build tooling around this, have people build tooling around these descriptors. So yes, absolutely. Totally agree.
And part of the approach also helps us, as well as the practitioners and researchers, identify there's some categories of mismatch or that will actually emerge because the field is new, you don't know some of the things you don't know, and eventually those will fall in place. But others are actually enduring challenges that we need to really more research on, and this kind of an approach allows us to separate, okay, some of these will eventually go away by themselves because the practices will be learned by all these individuals. There are other safeguards that are already out there that people will start employing. Others, and we've identified some of these, like for example, testing being one, that really requires more research from different individuals to actually advance the field and make these machine readable descriptors, define them, identify more of them, develop automation, and all the good stuff that comes with it.
Yeah, so Ipek, you mentioned testing there as if that's sort of a simple and one thing, right? But because of all of these different areas of mismatches, like there are different testing that's needed for maybe each of the pairing. So I imagine that there's some mismatch that are between data scientists and engineers, some mismatch between data scientists and ops, right? Some between ops and engineers, right? And so are there different tests sort of on each of those axes? And like, how do we go about making sure that the right people learn about the right tests?
Absolutely. And that's actually why we're going to do continuing work in this area, because the work we did just scratched the surface. And this happened coincidentally at the time when we were working with some organizations who happened to have challenges in what does it mean to test an ML model while it's being developed by data scientists? What does it mean to test that model when it's actually part of the system and when it's deployed? Are there techniques that are already applied by software engineers that are used, which is there? There are techniques that data scientists use, but it seems to be more of an art rather than a science in terms of how some of these organizations are going about that. So that's actually what we're going to be doing next. You're right. There are mismatches that we can safeguard. There are some, again, obvious methods that could be used, but there's also gaps that we need to identify and do more work on.
Grace, I don't know if the more interesting part for our listeners is the things that we can fix easily or the things that are going to be super hard to fix and we might be stuck with for a while. But maybe do you want to talk about maybe the good news first?
Sure.
And then the bad news?
Right. So here's the good news. The good news is that at a small scale, we were able to validate our findings. We were able to validate that mismatch exists. Yes, this is very important to share to avoid that mismatch. So the good thing is that for many of those mismatches, there's not really a rule that says this value has to equal this value. For many mismatches, just share the information. So for example, when you hand data to a data scientist, tell them more about it. Where did you collect it? How did you collect it? At what time was it? I mean, like just basic information. Or where did you get it from? When the model is operational, how fast is the data going to be coming into this model? So a lot of them, I would say, about 70% of them were really just sharing information. For others, we did have to build rules. So, for example, when a data scientist is building a model, it is a good idea if that data scientist has some information on what are the computing resources that are required to serve the model. But then you can have a formula, right? Meaning resources in operations have to be greater than resources required for running the model. So the good news is that a lot of it is really simply information sharing. For a lot of them, there are kind of simple rules, but there are areas that are still very difficult. So the number one cause of mismatch in our interviews was testing. It was really testing because we don't really know how to test these types of systems. And for example, from the data scientist perspective, when they say, yes, we tested the model, it basically means we evaluated the model and the model has the expected accuracy that we were targeting. For a data scientist, that is what means testing. For a software engineer, it's like, have you done unit testing? Have you done? Mm-hmm. And so the data scientist is like, oh, unit test, I'm not sure I know what that is. So part of the work that we're going to be doing next is really building on that, because that's what we saw there was like the biggest gap. So for example, how can we, through tooling, how can we help data scientists build unit tests? Something that they're just, I mean, it's nothing wrong. It's just that they weren't trained with that.
Yeah.
From a software engineer perspective, what does it mean to integrate a machine learning modeling, and what does integration testing look like? So I guess the bad news, although you could say it's good news, is there's so much work to be done.
Thanks, Grace. I think that the different testing stuff is really interesting. One of the things I was curious about reading your work is whether like the security side of these things falls under operations. So like I've been doing some thinking about how to manage vulnerabilities in ML enabled systems, which is sort of an operations problem. But the security community has sort of different testing, like fuzzing or symbolic execution or whatever sort of program verification stuff, similarly to do something similar to what unit tests are doing, but looking for sort of a different objective.
Mm-hmm. Right.
How do you think we can communicate those sorts of tests? I know that this isn't exactly what you did your research on, but can we sort of integrate all of that into the testing that we need to bring together with the mismatches?
So I think there are opportunities with the mismatch and the descriptors, both from a testing perspective, but there were other categories of mismatches that we've identified. Like, for example, the mismatch between development environment and operational environment would also provide opportunities to safeguard and catch for some of the issues that you're talking about. I would not probably lay them all on testing, but testing definitely will create opportunities to catch some of those.
Yeah, and also I would say that some of the let's call it security testing is testing that we've been doing forever and ever and ever. For example, validate your inputs. That is not a common practice in the data science community, right? But it's a very common practice in the security and the software engineering community. So really, it's really looking at what is out there and providing those tools that people that are not aware of what you need to do to make a secure system.
Yeah. So Ipek, can you talk a little bit more about the mismatch between the development environment and the production environment that you mentioned briefly there?
So some of the examples that we came across were, for example, when the ML models were being developed, this all happened both in the data science aspect and the software engineering aspect, the environment that they were collecting the data, running the model and whatnot was different from the actual operational environment. This was a huge resource consumption assumptions mismatch. Sometimes it works, sometimes it doesn't, but that created a lot of failures for some of the organizations that we talked to. And this is, I think, something that could easily both be checked as well as automated, because these things are, there are attributes for these that actually can be upfront or in an iterative way identified and brought back into the environment.
Okay, so can you, what is the, I know it's hard to briefly summarize the whole data lifecycle, but can you give us some highlights on where some of those data lifecycle mismatches show up?
Absolutely. So kind of like from a data life cycle, right? So you start out with raw data. The raw data gets processed, and you come up with training data and evaluation data, right? And then eventually the model gets put into production, and now you're dealing with operational data or production data, right? So there are lots of opportunities for mismatch, not only just related to the data, but also, again, related to the different categories. So, for example, a data scientist gets raw data. We heard it over and over again, the data scientist saying that somebody just tosses them a piece of data and says, go do some data science to this. Just go and do something. Tell me something about this data. And it's like, okay, what problem are you trying to solve? How will you know that the problem is being solved? So from that perspective, there are mismatches between the expectations, like from a product owner, of what the model of what a model could do, and what you actually can do with that data, if that makes any sense. So there are definitely mismatches there. Mismatches between let's say raw data and training data usually occur because there's not enough information about the raw data. Sure, you give me the raw data and it's field 52, field 53, field 73. And I'm the data scientist, I'm looking at this, I'm like, I have no idea what field 53 is. It might be that I may able to tell you something interesting about field 53, but unless I have more context, I really can't give you a good solution. Yeah. And then further on, okay, you have a trained model, everything is great. But what happens? Usually when a data science team trains a model, you're giving the data in some, let's call it static format, right? It's in a database, it's in a data file, it's in some data source. When that model is put into production, the data is not coming from a static data source, right? It's coming from a data stream. It's coming from user input. It's coming from another thing. And again, for the data science, if the data science team doesn't know, like, operationally, like what are the data rates? It's not only the data science team, but the software engineering team is not going to be able to say, yes, this model is performing well, but more not so much from an accuracy perspective, but from a performance perspective, like, producing inferences in an appropriate amount of time. So I hope that answers your question, but those are some of the mismatches related to data that we found.
Yeah, thanks, Grace. I think that is a good summary of the whole life cycle from data collection through forming hypothesis in a model and moving that into production and the stuff that can happen. Mm-hmm. I hear, some of this is essentially good scientific practice generally, like have a question like have a question you're trying to answer, like have a success criteria where you know whether you've answered it or not, like understand how it's going to change your model of the world or what you want to learn from it and why you care about it. Ipek, I know that Ipek, you've been involved in that more generally in software engineering, like through the journal that you're chief editor of and all of this. Like, you have a lot of different perspectives on this.
So it boils down to codification of best practices. There's a very important aspect of the ML mismatch work that is codification of the best practices. Some of these are experienced engineers, experienced data scientists already know, but it's really based on their experience. Once you codify, especially when you can codify and represent them as a descriptor and provide some form of ability to check regardless of who's doing it, that's really when you baseline some of these avoidable problems occur. That's really what it boils down to, and that's probably what is transferring from software engineering and software engineering from machine learning. That's really how software engineering has improved over the decades. And I think that information is transferring, and that's the approach we brought to the project as well.
So, Ipek, that's really good understanding of codification. So what are some of the remaining challenges for deploying, operating, and sustaining ML-enabled systems?
So one of the things, there are large industry organizations that have been using ML models and AI techniques as part of their software. They do it because they have resources, and some of the software that they produce are not as mission critical. One of the things I think, especially for our stakeholders within the DoD and more mission critical, safety critical domains, sustainment and maintaining these systems will actually going to probably pose new challenges. We don't know what we don't know there yet. We're mostly focused on the best use of algorithms, development algorithms, making sure that we improve the precision, their decision-making capability, ethics, bias, privacy, all these good things that are actually involved in developing ML-enabled systems. But once I think these systems are out there in the field, we'll start seeing some of their sustainment and deployment challenges. We'll see how we'll actually be able to upgrade. Some of the work we're doing in ML Mismatch will definitely contribute to that, but there's more work to be done in terms of how we monitor them, how we scale them, how we architect for them. Those are all, I think, going to be things that we'll learn more as we have more experience coming from the field as well.
That's great. So, Grace, can you talk a little bit about how those challenges that Ipek just mentioned might inform your future work or the future work of our colleagues here at the SEI?
Yeah, so absolutely. So one of the things that, first of all, we have upcoming work, in addition to building tooling around mismatch detection, like we said before, we're really focusing on testing, because that's a big issue, on providing support for testing for not only for data scientists, but also for software engineers and even operations folks. In addition to that, as people that have followed the SEI for many years, especially our software architecture work, we have a big emphasis on quality attributes, understanding a system through its quality attributes. What does security mean for a system? What does scalability mean for a system? And all the abilities you can think of. And one big quality attribute that is not new, but I really think it's going to be key for these types of systems, is monitorability. Just because if you think of the model, the model just, it only knows what it knew at training. If it starts seeing new data, it's not going to perform well. It might be that the environment itself changes, and so now the predictions are somewhat different. So being able to develop systems that have monitorability built in, so that you can tell that something is different in the system, I think that's going to be a is going to be a big challenge, like Ipek said, as systems are deployed. And it's something that we're definitely very interested in, given, like I said, our quality attribute focus. I just think that's one of those quality attributes that is going to emerge. Another type of quality attribute is that, we talk about ethics a lot, right? In AI and ethics, I know that's a big theme. But what does ethics mean from a quality attribute perspective? Like, how do I build a system that shows that it is ethical? How do I say this design is more ethical than this other design? So it's understanding those new requirements and quality attributes that come from this field. I think that's also a very interesting area of research that we would like to explore.
And we have efforts going on in all those areas, in addition to those that Grace mentioned. Understanding how to move these into operations, there's all the new work coming in ML ops, but there are missing parts of the life cycle, and that actually meets well with the monitorability. How do you actually provide some of the information to the operations as well as data scientists throughout the life cycles?
Thanks, Grace. Thanks, Ipek. I have, a number of topics that I know that we could spin off to on those two things that you just said. What is ethics from a quality attributes point of view is an amazing question that I think we could probably talk about for another hour. But before we go
next podcast.
Before we go too far off into something like that, I think it's important to understand, what we can transfer to practice sort of right now out of what we already know. So for our listeners that are software engineers or machine learning engineers or operations people who are getting engaged with an ML system, like, what resources are available to those listeners to sort of do a little bit better right now?
Okay, so part one of this research project, which was characterizing and understanding mismatch, was presented in an SEI webinar. So I would definitely start there. It's available on the SEI website. Just go to the SEI website, search for software engineering for machine learning under the webinar series. Now, the paper that describes the methodology more in detail was recently delivered and published at a brand new ICSE 2021 workshop on AI engineering called WAIN, WAIN 2021. And a preprint of that paper is available on archive. It's called Characterizing and Detecting Mismatch in ML-Enabled Systems. So obviously you can look on archive for that. And finally, the replication package for part one of the study, if you're interested in seeing the actual data and what the mismatches were, it's available on GitHub on github.com /GA Lewis/ML-mismatch. And the plan is to very soon, Ipek and I are working on that, is to upload the replication package for part two, which is also going to include the resulting descriptors, which I think are the main outcome of this project. And I think that's going to bring, it's our belief that it's going to bring a lot of benefit, especially to practitioners of the field.
That's great. And we'll definitely have links to all of those resources in the show notes, so our listeners don't have to sort of rewind and scribble that down. So everyone can go to the show notes and you'll find links to all of those wonderful resources that Grace just mentioned. Ipek, is there anything else that you think our listeners should know right now about what they can maybe do a little bit better sort of with what we have available right now?
So I think the SEI puts out some of the results of the early work out there. I would encourage listeners to visit our website and blog regularly. There are also other things that have been published. You mentioned IEEE software. There was a special issue focusing on AI effect, and there were some interesting papers that relate to what we've done. We published 11 practices for AI engineering. I think those resources could also be starting points for practitioners or researchers who are starting to think about applying software engineering to ML-enabled systems, as well as thinking about AI engineering.
Yeah, that 11 good practices document is definitely a good place to start.
And in addition, recently SEI has published the 3 pillars of AI engineering, which include robust and secure AI, scalable AI, and human-machine teaming. I think those are also available, and they're good resources to get started.
Great. So, Grace, Ipek, thank you so much for taking your time to talk with us today. And thank you to all our listeners for joining us. We'll have links to all of the various things that we've mentioned during the podcast in the show notes. And Grace, Ipek, thank you very much.
Thanks for joining us. This episode is available where you download podcasts, including SoundCloud, Stitcher, TuneIn Radio, Google Podcasts, and Apple Podcasts. It is also available on the SEI website at sei.cmu.edu/podcasts and the SEI's YouTube channel. This copyrighted work is made available through the Software Engineering Institute, a federally funded research and development center sponsored by the U.S. Department of Defense. For more information about the SEI and this work, please visit www.sei.cmu.edu. As always, if you have any questions, please don't hesitate to email us at info@sei.cmu.edu. Thank you.